In this video, we're going to talk about subset relations. In other words, how various subsets are related to each other and to sets. So we're going to start by talking about the inclusion of intersection. So we're talking about an intersection right now. So let's look at our example right here, our little Venn diagram. The inclusion or the intersection is going to be this middle region where the two A and B overlap. Right? So this is going to be A intersect B. So what do we know about this region? Well, we know that, for example, A intersect B is a subset of A. Right? Because this region that we've filled in here on this diagram is part of A. So I can say it's a subset of A. We can also say that A intersect B is a subset of B. We can even, if we feel so inclined, prove this. So proof, I'm going to use the element method. And I'm going to do a direct proof. So I'm going to suppose that A and B, right, I want to start very general. A and B are any sets. And suppose that X is any element in A intersect B. Right, so we've got, it's hard to see right here, but I've colored this in too much, but there's X. Right, so that's X right there. Well, what do we know? We know then by the intersection, by the definition of intersection, we know that X is an element of A and X is an element of B. Right? And again, you can go back to a previous video where we defined intersection, and you can look at the formal definition, and I believe it says that A intersect B if and only if X, how would we write this? X is an element of A intersect B if and only if X is an element of A and X is an element of B. All right, so since we know that X is any element in A intersect B, then I'm looking down here at the proof now, then by the definition, I know that X is an element of A and that X is an element of B. And since X is an element of A, for any X in A intersect B, right, then recall the definition of subset. Right? We say A is a subset of B if and only if for all X in A, X is in B. So since X is an element, so looking back at my proof now, since X is an element of A for any X in the intersection, then the intersection is a subset of A. So I just proved this first relationship. but a very pretty much identical proof can be used to prove the second relationship. And again, we're proving this by the element method. And the element method can be summarized as looking at an element that's generic enough to fit into whatever set we're talking about. And then it usually involves a lot of definitions. So here we've got the definition of intersection. And then here we're using the definition of subset. Now let's talk about the inclusion of union. So again, if we recall, A union B is going to be all of this. Right, this is A union B. So we have the following relationships. A is a subset of A union B, and B is a subset of A union B. And again, looking at this makes sense. So if we take A is part of the overall shaded region, right? And B is part of the overall shaded region. So they're both subsets of the overall shaded region. But we can prove this more formally using the element method. And we can say, suppose A and B are any sets, and suppose X is any element in A. All right, we're keeping things general. So here we've got X. Then, by the definition, see again, we pick an element and then we use definitions. By the definition of union, X is an element of A union B if and only if X is in A or X is in B. Oh, that's wrong then. This is by the definition of union, X is an element of A union B if and only if X is an element of A or X is an element of B. And since X is an element of A, we know that X is an element of A union B. Now, by the definition of subset, we can say A is a subset of A union B. And again, if you're a little confused by that, you can go back to the previous video where we defined subsets. But again, we said that A is a subset of B if and only if for all elements X in A, X is also in B. And we just said that X is in A, and we kept X very generic. We used any. So that lets it say it doesn't matter what X. We just know X is in A, meaning it must be in A union B by the definition of union. So we know we fulfill this relationship, this subset definition, and we can conclude that A is a subset of A union B. And finally, we're going to talk about one more property. This is the transitive property. Here's the way this works. I'm going to make a claim. I'm going to say if A is a subset of B, all right, so over here we've got B, here's A, and B is a subset of C, then A is a subset of C. And I think that's pretty clear from this diagram, right? Everything in A is also going to be in C. So we could call this a Venn proof. But to be a little bit more rigorous, we can also prove it more formally. I'm going to do a proof by contradiction. Now, with the element method, we're going to be using the element method, we can use any proof type. We've seen direct proofs. We can do proof by contradiction. We could do proofs by contraposition. We could even do inductive proofs if it made sense. Okay, so what I want to do is, again, I'm claiming that if A is in B and B is in C, then A is in C. I'm going to suppose so again, this is going to be P and Q implies R. So to negate this, it's going to be P and Q and not R. Right? Recalling how we do implications. Don't forget this stuff. So I'm going to suppose that A is a subset of B and that B is a subset of C and that A is not a subset of C. Well, what does that mean? Well, if A is not a subset of C, we know what that, we have a definition for that. You could say, then there exists an element X such that X is an element of A and X is not an element of C. Right? That's what the definition means. That's what it means when we say not a subset of. So we can then say because A is a subset of B, right? That's part of our supposition. We know that any X, let's draw this X. Here's the little X in our illustration. Because X is a subset of B, we know, or excuse me, because A is a subset of B, we know that X is an element in B as well. And this is by the definition of a subset. Well, because X is an element in B and B is a subset of C, right? And again, this is something we're supposing right there. X is an element of C by the definition of a subset. But we defined X to not be in C, right? That's what we said here. So we have our contradiction. So therefore, if A is a subset of B and B is a subset of C, then we can conclude that A is a subset of C. And again, I think this illustration really shows this. We're going to see more later this semester about the transitive property. The transitive property shows up in a couple of different places. And it's usually this idea of passing a relationship along.